Welcome to the Royal Astronomical Society's ordinary meeting, a special one on this 19th of November. This meeting, as you know by now, is taking place via webinar. If you look in the top left of your screen, you should see a small green shield. That means you're using the most up-to-date version of Zoom and that it is secure. Now, during the lecture, if you want to ask questions, they can be asked at the end, but as you'll be muted, please use the chat facility found at the bottom of your screen. So put your questions on the chat facility. Your questions will only go to the panelists and they will be read out at the end by editorial team member, Dr. Pamela Rowden. Now, a couple of important deadlines I'd like to just mention to fellows. Elections to council. Can I remind you to propose a colleague or put yourself forward for election to council? The deadline for nominations is Friday, the 26th of November. Council would encourage all nominations, all welcome, either yourself or a colleague who you'd like to recommend. I'd also like to remind you of the RAS prizes for the best PhD theses in astronomy and geophysics that have been submitted in the calendar year 2021. These are prizes for the best theses in astronomy and astrophysics, the Michael Penston Prize, and in solar system sciences and geophysics, the Keith Runcorn Prize, and the instrumentation prize, the Patricia Tompkins Prize. The closing dates for nomination for these awards, which carry a cash prize of £1,000 each, and the opportunity to make a presentation at a future ordinary meeting, is the 31st of January next year. That's the 31st of January, 2022. Please do propose for those. Well, now on to today's program. We're holding today the 2019 Jeffreys Lecture, obviously carried over because of the pandemic. And I'm absolutely delighted to be able to welcome Francis Nimmo from the University of California at Santa Cruz, who's going to talk about 3 surprises from planetary science. Francis Nimmo received his BA in 1993 and PhD in 1996, both from Cambridge. He was Royal Society University Research Fellow at University College London before joining the Santa Cruz University of California facility in 2005. In 2007, he received the Macelwane Medal of the American Geophysical Union and the Urey Prize from the Department of Planetary Science of the American Astronomical Society. His interests cover the interior and evolution of rocky planets and moons. So it's my great pleasure to introduce Francis to give the Jeffreys Lecture.
Thank you very much, Mike. And I'm sad that I can't be with you in person. So, as Mike said, what I want to discuss is 3 things that I think are surprising in planetary sciences. But to begin with, I want to back up a little and to just explain what I think planetary science is. And so, if we look at the objects in this solar system, the really striking thing is the amount of diversity that you see. To an astronomer, Venus and the Earth would be essentially identical. They're the same mass and the same radius. And yet, from a geophysical perspective, they're totally different objects. The Earth has a magnetic field, Venus does not. Earth is wet, Venus is dry. If you look at Uranus and Neptune, they again appear astronomically identical, but one is letting out a lot of its internal heat and the other is not. And so everywhere we look in the solar system, we see unexpected diversity. And so in my view, what planetary science really tries to do is it tries to understand the processes that led to this incredible diversity that we see at the present day. And so obviously it's an observational science, just like astronomy. And so you can't run experiments, but what you can do is you can make predictions. And every so often a prediction is spectacularly vindicated. Perhaps the best example is that Io, the innermost moon of Jupiter, was predicted to be volcanically active shortly before the first images were returned. And this is a more recent image showing this volcanic plume extending a couple of 100 kilometers above the surface. And so we can make theories, and those theories can be tested. Compared to astronomers, we're very data starved in the sense that we don't have many objects. There are 4 terrestrial planets, maybe a couple of dozen of interesting moons, but there aren't thousands of objects that we can study. On the other hand, I would argue that in some senses, planets are more complicated beasts than stars. For one thing, they're made of more elements, and also they operate at lower temperatures. And so I think the problems are more complex. And then lastly, even though the technology that we use is really extraordinary, who would have thought that we would be flying helicopters on Mars? The physics that we use to probe these planets is very much 19th century. Somebody like Maxwell would have no problem understanding the theories that we're using. So this is the Jeffreys lecture. And so, of course, one of the things for which Jeffreys is famous was thinking about the internal structure and the evolution of the Earth. That's something that I'm interested in too. And these days, one can also think about the internal structure and the evolution of other planetary bodies, not just the Earth. And so what I'm going to talk about is how things have changed over the course of my career, which at this point is a quarter century. And so I'm going to highlight 3 of the big changes that I've seen. One change that I'm not going to talk about at all is probably the most important change, and that's the discovery of exoplanets. When I was at school, the number of confirmed exoplanets oscillated between 0 and 1. And now, of course, we know that there are thousands of these things. But I'm not going to talk about that because I'm more interested in places we can send spacecraft to. And so the 3 surprises I'm going to talk about, one has to do with the rotational state of planets. The second has to do with the existence of subsurface oceans in the outer solar system. And the third has to do with the generation of magnetic fields inside these objects. And so I'll spend the rest of the lecture talking about these 3 topics. And one of the things that you'll notice is that although observations are key, there is also a role for both theory and lab experiments in all 3 of these topics. So let me jump straight in and to start talking about the fact that planets are wobbly. And as I'll explain, the main reason that we care about this is that if you can measure the rotational dynamics of a planet, that tells you something about their internal structure. This is also an interesting story in the sense that the big advances actually came through a theoretical development rather than primarily any kind of observations. So let me start with one particular form of rotational behavior. This is called the Chandler wobble. So if you're standing on the Earth is rotating about a spin axis. And so you can stand somewhere and look at a star and measure its angle. You can measure your angular position relative to the star. If you come back and do the same thing a little later, the star will appear to have moved. But of course, in fact, what's actually happening is that the solid surface of the Earth is moving slightly relative to the spin axis. And if you continue to do this, you see that there's a backwards and forwards periodic wobble of the solid Earth relative to the spin axis. And this is known as the Chandler wobble, and it was discovered in the late 1800s. The interesting thing about the Chandler wobble is not so much its amplitude, which is a few meters, but it's the period. And it turns out that the period is not the period you would predict for a solid Earth. And so the measurement of the Chandler wobble period told us something very important about the inside of the Earth, that it had to have a fluid component. So you've learned something about the interior. Now, more recently, exactly the same thing has been done for Mars. If you watch Mars for a while, then you see that it too exhibits a Chandler wobble. But the really remarkable thing here is the amplitude of the Chandler wobble, which is 10 centimeters. And so this is remarkable. This is a triumph of geodesy, that you can measure this tiny motion on a different planet. And again, the period of the Chandler wobble can be used to make inferences about the internal structure of Mars. Okay, that's one class of motion. The class of motion that I really want to talk about is called, for historical reasons, true polar wander. And in this case, rather than having a periodic motion, what happens is you have a secular motion that the solid surface of the Earth slips relative to the rotation axis. And these motions can be large, they can be, tens of degrees. So it's a secular motion, it's not a periodic motion. And the reason that it's important is that it can move very significant distances on the surface of the planet. And so there are a couple of places where people had hypothesized that true polar wander had happened. One good example of is Mars. This is a topographic map of Mars. You can see that Mars has this massive volcanic bulge, the Tharsis bulge, which is located more or less on the equator. And that's what you'd expect from true polar wander theory, as I'll explain in a minute. And in the outer solar system, there's this extraordinary moon called Miranda, which has these bizarre geological features called coronae that line up with its axes of inertia. And again, that's what you'd expect from true polar wander theory. So the way the theory works is that if you have a planet that's rotating, it develops an equatorial bulge. And then if you stick an extra mass onto the surface of that planet, that changes the moments of inertia of the planet, and the planet will respond. And the way to minimize the overall rotational energy is for that extra mass to move towards the equator. And so if you add an extra mass to a planet, the planet reorients to move the mass towards the equator. Conversely, if you take a planet and you dig a hole out of it, then by the same argument, that mass deficit will move towards the pole. Now, that motion towards the equator has moved the original equator off its original position. And so if any part of that equatorial bulge is frozen in, then it won't want to move off the equator. There will be a torque trying to restore it. And so there's actually a competition between the size of the load and the size of this fossil bulge. So the load promotes reorientation, but if there's a fossil bulge, that opposes reorientation. And this was understood in the 1980s, but it turns out that the theory was actually in error. There was a sort of rather subtle mistake that had been made, and this error was only corrected in 2006. Once that error was corrected, people began to start to think seriously about whether true polar wander might actually have happened. The big problem, of course, with true polar wander is that it's not like the Chandler wobble. You're not seeing it happen. You have to look for evidence in the geological record. And so that's generally hard to do. But I'm going to discuss one case where I think there actually is some geological evidence that it did happen. And so that is at Pluto. And so before 2015, we knew almost nothing about Pluto. This is our best pre-2015 image of Pluto taken by Hubble, and you can see that it's about 6 pixels across. After 2015, the New Horizons spacecraft visited Pluto, and we get magnificent images like this. So Pluto moved from being an astronomical object to a geological object. And the area that I'm going to focus on is this bright region here called Sputnik Planitia. So this is a close-up of Sputnik Planitia. What it is, it's a big basin, probably an impact basin, filled with nitrogen ice. And if you look at the nitrogen ice, you can see it has this wonderful cellular structure, which means that it's probably convecting just like porridge on a stove. And then over here, this is just topography of the Sputnik Planitia region. And you can see that indeed it's a flat-floored basin surrounded by mountains. Now, the interesting thing about Sputnik Planitia is its position. This is a projection of Pluto, and the cross is the present-day center of Sputnik Planitia. And you can see that it's very close to the 0 latitude, 180-degree longitude. This is a point through which the tidal axis, the line joining Pluto and Charon, goes through. And so this seems suspicious. It might just be there by chance, but if it were the case that Sputnik Planitia represented a mass excess, then if it had started somewhere else, true polar wander would have moved it towards that tidal axis. So the present day location of Sputnik Planitia suggests that true polar wander may have happened. It may have started somewhere else, and then Pluto will have tilted over to move it towards the tidal axis. But that only works if Sputnik Planitia represents a mass excess, a positive gravity anomaly. Now, if you've been paying attention, you will say, well, Sputnik Planitia is a hole in the ground. How can it possibly represent a positive gravity anomaly? And that's a good question, but it turns out that we know other places in the solar system where we see holes in the ground that represent positive gravity anomalies. And these are impact basins on the moon. They're called mass cons for mass concentration. And this is just an example. This is Mare Smithy. You can see that it's a hole in the ground, but it represents a positive gravity anomaly. And we understand more or less how these things work. And the answer is as follows. You have an impact. The impact scoops out a lot of the surface, which either be crust of the moon or the ice shell of Pluto. And so you end up with a thin shell. Now, the pressure at the bottom of that shell will be less than the pressure somewhere else. And so basically, by Archimedes' principle, the shell locally will get pushed back up to retain equilibrium. And so you'll end up with a bulge of the ocean underneath the thinned shell. If you then sit there for a while and let your crust become cold and rigid, then if you pour lava or nitrogen onto the surface, it will fill up the basin, and that then will represent a mass excess. And so by this process, you can end up with a positive gravity anomaly, even though you have a hole in the ground. And so Sputnik Planitia could represent a positive gravity anomaly as long as there's a subsurface ocean. And that positive gravity anomaly may have reoriented Sputnik Planitia towards the tidal axis. So this is a nice fairy story. Is there any evidence that this actually happened? Well, there is some, and that comes from looking at the tectonics of Pluto. And so on the bottom, what is being shown is predicted faults as a result of true polar wander. The reason that you get faulting is that as the body reorients itself, some parts of the surface will drift over the bulge, and so they'll get stretched. Other parts will get compressed. And so there's going to be a predictable set of tectonic features that you'll get as a result of the reorientation. And so on the bottom are the predicted orientation of the faults, and on the top are the actual faults that have been mapped on Pluto. And you can see that there's a reasonable agreement. It's not perfect by any means, but for instance, this swath over here agrees quite nicely with the swath down here, and so on. And so it's been argued that the arrangement of tectonic features on Pluto is evidence that true polar wander actually happened. It would be nice to test this in other ways, and one very obvious test is that I just told you Sputnik Planitia is a positive gravity anomaly. And so in principle, all we need to do is we need to send an orbiter to Pluto, and then we can measure the gravity anomaly. Now, it turns out that this is possible, but it takes about 40 years to get there, and it involves rather more plutonium than NASA is likely to have. But nonetheless, at least in principle, this is a testable hypothesis. Okay, so true polar wander is expected to be quite common. And at least at Pluto, I think there's reasonable evidence that it actually happened. If it did happen, then the implication is that Pluto has a subsurface ocean. And so that leads me neatly into my second topic, which is the prevalence of ocean worlds in this solar system. So this is a plot of the moons of the outer solar system with our own moon for scale. And what I've done is I've colored in the moons blue where we're pretty certain a subsurface ocean exists. And there are 3 Galilean satellites, Enceladus and Titan at Saturn. And the really striking thing is that in 1995, we didn't know that any of these bodies supported subsurface oceans. So this has been a very big change in the last quarter century, the prevalence of subsurface oceans. Why do we care about this? The main reason is astrobiology. Subsurface oceans are places where things might live, and NASA, at least, is very interested in looking for life. Now, nobody really thinks that there are going to be squid moving around in the subsurface. Nonetheless, the search for life is one of the big focuses of NASA. From my perspective, the important point is that if there's a subsurface ocean, that tells you something about the thermal evolution of the body. It's had to stay warm enough for long enough to generate and maintain a subsurface ocean. So it's a clue to the thermal history of these moons. So what I'm going to do is I'm going to talk you through very quickly some of the ways that these oceans have been detected. And I'm going to spend a little more time on the last one, the study of obliquity, just because that's something that I've thought about a bit. But I'm going to start out with really the most elegant technique that has to do with induction. And so the way this works is that Jupiter's magnetic field is tilted, just like the Earth's. And so as Jupiter rotates, the magnetic field spins around. And if you're a satellite, you feel the changing magnetic field as Jupiter's magnetic field gets swept past you. Now, if the satellite is conductive, a changing magnetic field with a conductor induces a current, and that current will produce a secondary magnetic field. And the secondary magnetic field is something that a spacecraft flying by can measure. And so this is just a picture. You have the primary time-varying magnetic field in the solid lines. That induces eddy currents. The eddy currents induce a secondary magnetic field that opposes the primary field. That can be measured by a spacecraft. And this was done at Europa, and an induced field was detected, and it was consistent with the existence of an ocean, and a conductive ocean, a salty ocean beneath the surface. And so this is a very clever technique. And in fact, further examinations show that not only Europa, but also Ganymede and Callisto almost certainly have oceans beneath their icy surfaces. So they all have subsurface oceans. Ganymede is interesting because it also has not just a time-varying inductive field, but it also has a permanent field. And so Ganymede apparently has some kind of magnetic field generating mechanism, a dynamo inside it. And then Io has no ice at all, but Io also showed an induction signature. And there the answer must be that it has a partially molten rocky interior. Partially molten rock is also electrically conductive. So this is a very powerful technique. It won't work at Saturn, unfortunately, because Saturn's magnetic field is not tilted, but it would work extremely well at either Uranus or Neptune. So this is a good general technique for looking for satellite oceans. Something else we can use is the fact that satellites experience tides. If you have a moon next to a large planet, then the near surface of the moon experiences a slightly bigger gravitational force, the far side experiences a smaller force, and so the net result is that the moon gets distorted. And if the distance between the moon and the planet changes, that distortion will change. And so the tidal bulge will grow and shrink and grow and shrink. And that's ultimately what causes tidal heating. And so this is just what I'm showing here. When you're far away from the planet, you're less distorted. When you're close to the planet, you're more distorted. If you take this diagram and you convert the reference frame to that of the moon, what you see is that the planet in the reference frame of the moon moves backwards and forwards over time. It executes a little ellipse in the sky overhead. And one of the reasons that that's important is that that will actually generate torques on the satellite. Over the course of each orbit, there will be clockwise and counterclockwise torques acting on the satellite to change its rotation rate. And so in an eccentric orbit, you expect the rotation rate to be variable. It's not going to be constant. And this variation in rotation rate is called a libration. It's a periodic variation in the rotation rate. The really useful thing about librations is that the amplitude of the libration tells you about the inside of the satellite. If your moon is solid, then the torque is being applied to the whole body, and so you'll get a small libration. But if the moon has an ocean inside, then the torque will only be applied to the shell, which has a smaller moment of inertia, and so the libration amplitude will be larger. And so simply by measuring the amplitude of the libration, you can tell whether a moon has an ocean or not. And this is actually our best evidence that the moon Enceladus has an ocean. Here is Enceladus with the UK for scale. You can see that Enceladus is rather a small object. Nonetheless, it has an ocean, and we know that because of the detection of large librations. Something else we can do with tides is to look at the amplitude of the tidal response, how much the bulge changes over the course of an object. And that's described by these dimensionless Love numbers after A.E.H. Love. Here he is with a splendid moustache. I recently found out that he actually went to the same school as I did, but I'm not going to be growing a moustache like that. Again, if you have a liquid layer, then that increases the deformation. And so by measuring the tidal response, you can tell whether or not an ocean is present. So if you have a satellite where the ice is bonded to the rock, you get a small tidal response. Whereas if you have a decoupling ocean layer, then the tidal response is much larger. And so by measuring the tidal response, you can tell whether an ocean is present or not. And for these purposes, K2 is very convenient because it just involves changes in the gravity. And so that's relatively easy to measure if you have a spacecraft in orbit. And so in the case of Titan, which is the big moon of Saturn, Titan's K2 is so large that really suggests an ocean is present. In fact, that's not the best evidence we have for an ocean, though. And so I want to talk about obliquity, because that's the best evidence for an ocean on Titan. So let me talk about obliquity. Obliquity is just the tilt of a moon or a planet. And so in the case of the moon, this is the geometry. We have a planet with a spin axis and an equator plane. And in general, the orbit of the moon will be inclined to that equator axis. And so the orbit normal is not parallel to the spin axis of the planet. Furthermore, the spin of the moon may not be parallel to, the spin axis is not parallel to the orbit normal. And so there's a tilt. This is the obliquity. The obliquity is just the offset between the spin axis and the orbit normal. That's the obliquity. Now, for planets, that obliquity is more or less a free parameter. But it turns out that for all the important moons, the obliquity is not a free parameter. It's actually fixed by other aspects of the moon. And that's because all these moons occupy something called a Cassini state. So let me try and explain that. Here are these three vectors again. This is the spin axis of the planet, the orbit normal, and the spin normal, shown in 3D space. And at some point, those three vectors will line up. They'll be coplanar. Now, orbits precess, and so the orbit normal is going to precess around this black vector, and spin axes precess, and so the spin normal is going to precess around the orbit normal. So the orbit normal is going to precess like that, and the spin normal is going to precess around the orbit normal. But it turns out that all the big moons, they don't just precess randomly, they precess in such a way that the spin normal and the orbit normal remain coplanar. And so they were coplanar here, they precess, and they remain coplanar. And the reason for doing this is that this is the state which minimizes the dissipation. And so this is what's called a Cassini state. And it means that the obliquity is not independently variable. It depends on other things. And in particular, it depends on the moment of inertia of the satellite, and it depends on the torques that the planet is applying. So the obliquity depends on the torques and the moment of inertia. If we can measure the obliquity and we can measure the torques, then that tells us the moment of inertia of the satellite, which is what we're really interested in, because that tells us about the internal structure. The moments of inertia depend on the obliquity and the torques. The torques depend on the gravity, which we can also measure. So if we measure the obliquity, we measure the gravity, we can get the moment of inertia. So that's just the same plot I showed before. Now let me show you some real data. So this is just a projection of Titan's spin and orbit poles. It's like the top of this diagram. You can see that the orbit normal is precessing. Here's the present day orbit normal. We know Titan's gravity, and so we can predict what the spin normal should be doing. And if Titan was solid, the spin normal would be doing this, and the obliquity would be that. But we've measured the obliquity, and the obliquity is here. And so what Titan actually does is its spin normal does this, and so the obliquity is a factor of about 3 larger than it should be for a solid Titan. So that's a very big discrepancy. The obliquity is much larger than you expect, and really the only sensible solution is that the torques are acting on a shell, not on the whole body, so the moment of inertia is smaller, and so the obliquity is larger. And so this indicates that the shell is decoupled from the interior by an ocean. And so this is the best evidence that Titan has an internal ocean. The other lovely thing about obliquity is that in some cases, you don't even need to send a spacecraft there. You can actually make these measurements from the Earth. So using the obliquity is a very powerful technique. Okay, so this is where we started. All I'm going to do now is I'm going to add the methods by which we know these objects have oceans. For the 3 Galilean satellites, we use induction. For Enceladus, we know there's an ocean because of the libration amplitude. For Titan, we know there's an ocean because of the obliquity and the tidal response. And then I've added Pluto with a question mark because true polar wander is not as strong an argument as these other observations. As I said at the beginning, the reason I care about this is because of the thermal evolution of these bodies. And so what I'm showing here is 3 objects to scale. Here's Pluto, here's Charon, and Enceladus. And then on the right, I'm showing thermal evolution models. And so what's being plotted is the radial distance against time, and the colors and the contours are just temperature. And so in the case of Pluto, we have ice on the outside, rock on the inside. The rock has radioactive elements in it, and so the inside of Pluto heats up. It conducts heat outwards into the ice shell, and at some point, the ice shell gets heated up so much that it melts, and an ocean forms. And that ocean is sustained by heat leaking out of the interior. As the radioactive elements decay, the interior starts to cool, and the ocean begins to refreeze. But you can see there's no particular difficulty in maintaining an ocean on Pluto the present day. Charon is half the size, and so heat comes out faster, and there's less heat being produced on the inside. And so Charon produces an ocean, but the ocean refreezes relatively quickly. And so there's no ocean on Charon at the present day. And then Enceladus is so tiny that there's no way radioactive heat could produce an ocean. Nonetheless, it has an ocean. And so what must be happening is that it's being tidally heated, although the exact details of how this works are still not well understood at all. We could also think about the Uranian satellites, which are not well studied. Some of them are a bit larger than Charon. And so if you look at the case of Titania, for instance, this is the same kind of model, ice on the outside, rock on the inside. Again, the inside heats up, you generate an ocean, and you can see that in the case of Titania, it's marginal, it's right on the edge. Depending on how you tweak parameters, Titania could have a present-day ocean or not. Okay, the final topic I'm going to cover is dynamos. And so in a planetary context, what we mean by a dynamo is the set of processes that generate a long-lived magnetic field inside a body. And what's required for that is that you have an electrically conductive liquid in vigorous motion such that any seed field, the fluid wraps the magnetic field around itself and could generate a secondary magnetic field. And so it becomes a self-amplifying system. And so this is just an example of the magnetic field lines from some work by Gary Glatzmeyer. What's the inside these dashed lines is the fluid core of the Earth. And you can see that the field lines are all tangled and twisted around each other because this is the area in which the magnetic field generation is actually happening. So we need to have a fluid electrically conductive body in vigorous motion. And for terrestrial planets, what that means is that in general, you have to have convection in the iron core. And in order for convection to happen, you have to be pulling heat out of the core. And so here's a sketch. Here's the outer core, the liquid bit. If you pull heat out of the core, that cools the iron near the top of the core. It becomes dense, it sinks, and that's what drives convection. You might also be having an inner core, but that's not really necessary. What's really necessary is that you're pulling heat out of the top of the core to drive thermal convection. And so it's extraction of heat into the mantle that really matters. And so the reason that this is important is that the presence or absence of a dynamo is telling us about conditions in the mantle. Is the mantle pulling a lot of heat out of the core or not? And so this is a very useful marker if you're interested about the thermal evolution of these planets. So dynamos are a signal of planetary thermal evolution. That's why they're useful. And this is a situation in which, although remote sensing observations are quite useful, really a lot of what we understand actually comes from laboratory measurements, either of meteorites or even better, of return samples. And so, for instance, the Apollo astronauts brought back a lot of samples from the moon, and that's why we understand the moon's magnetic history rather well. So in 1995, this is more or less what we knew. Of course, the Earth has a magnetic field, Venus doesn't, and Mercury does have a magnetic field somewhat similar to the Earth's. The moon's magnetic field was not terribly well characterized at this stage, although it was known that there were magnetized lunar rocks. What's happened since then is that the magnetic field of the moon has come into much sharper focus. We discovered local magnetic anomalies on Mars, and we also discovered the fact, as I mentioned, that Ganymede has its own internal dynamo. And finally, there's also now a lot of evidence that the early asteroid belt was full of little objects producing their own magnetic fields. So the playing field has greatly expanded over the last 25 years. And I'll talk a little about some of these topics, but the one that I'll focus on again is the moon, because I've thought about that a little. So for Mars, this was one of the big discoveries, that Mars doesn't have a global magnetic field, but it has local magnetic anomalies, which are very strong. They're 10 times stronger than the strongest magnetic anomalies on the Earth. And in some areas, if you look over here, there was a hint that they might be stripy. And of course, that was extremely interesting because magnetic stripes on the Earth are a signal of plate tectonics. It was also pointed out that if Mars had early plate tectonics, that would be a very good way of cooling the mantle and sucking heat out of the core. And so plate tectonics on Mars could have driven a dynamo, and then when plate tectonics stopped, that would have killed the dynamo. And so there's this link between plate tectonics and dynamo activity. Venus is another example of this same set of phenomena. This is a topographic map of Venus, and what you can see is that there aren't anything like the long mid-ocean ridges that we see on the Earth. And so as far as we can tell, Venus has no plate tectonics at present. That means that it is not being cooled very effectively. Plate tectonics is a very efficient way of cooling the interior. In the absence of plate tectonics, the interior doesn't cool very rapidly. So you're not pulling a lot of heat out of the mantle, out of the core. And so it's very hard to operate a dynamo. And so the absence of plate tectonics can explain the absence of a dynamo. Okay, why does Venus not have plate tectonics? Well, on the Earth, we think that water makes faults weak. You get things like serpentinization or talc that lubricates the faults and lets them move past each other. If you don't have that water, if you don't have that lubrication, the fault friction may be too high to allow lateral motion of the plates. And Venus, of course, doesn't have any water. And so there's this rather seductive logic chain that goes like this. Venus has no water, and so it has no plate tectonics. And Venus has no plate tonics, and so that's why it doesn't have a dynamo. And so this is not an obvious set of connections. You would not a priori think that the absence of water would lead to an absence of a dynamo, but that may well be what's actually happening. Okay, lastly, let me come to the moon. For the moon, we have slightly better data because we have samples. And so this is just a plot showing the inferred field strength of the moon as a function of time. And the Earth's field for reference is about 30 microteslas. So the moon had a strong field early on, and then In the middle, it may have had a weak field, and then at some point, that dynamo died. So this is quite complicated behavior. And as a result, there's been a sort of cottage industry of different ways of explaining the lunar dynamo history. And so I'm only going to talk about one, and that is the idea of a mechanically driven dynamo, a dynamo forced by precession and not forced by thermal convection at all. And the argument goes like this, that the moon is distorted, and so its mantle, because of the torques from the Earth, precesses relatively rapidly. The mantle precesses, the core too will try and precess, but if the precession rate is too fast, then by the time the core has sort of moved itself around to the present day spin axis, the mantle spin axis will have already moved somewhere else. And so the core can't keep up. And so you may end up with a situation in which the mantle and the core are experiencing relative motion. And so effectively, the mantle is depositing kinetic energy into the core. It's stirring the core up. And so you can get a situation in which the precession of the mantle is driving the motion of the core. And this is actually very advantageous for a lunar dynamo because the lunar core is very small, and so it represents a rather small reservoir of thermal energy. But if you're driving it mechanically by precession, you basically have the entire energy of the lunar orbit to call on. So there's a much larger energy reservoir available. You can keep the core going for much longer. You can get a much larger dynamo. The other advantage of this suggestion is that as the moon moves away from the Earth, the precession rate changes. And so you actually end up with a situation in which the core naturally starts precessing with the mantle. And at that point, it's not getting stirred and the dynamo will die. And so the dynamo naturally dies as the moon moves away from the Earth. So I think this is a quite attractive way of explaining the lunar dynamo. And so here's just a summary showing what we know now. This is body size and time. And so for the Earth, we know that the Earth's had a magnetic field that's been long-lived. It may have started only a couple of 100 million years after solar system formation. Mercury, we don't know how long the field has lived, but it has ancient magnetic stripes, a little like Mars. Mars had a strong field early on that died at some point. The moon had a strong field that then became weaker and then at some point died altogether. And various asteroids had early magnetic fields. And so we know a lot about the magnetic history of the solar system. And really the main point is that this field history tells us about the thermal evolution of these bodies. Okay, let me wrap up. So I gave you 3 surprises. And the first is that planets are wobbly. That tells us about their internal structure, like the Chandler wobble. And I think that on Pluto, this is evidence for a subsurface ocean. A big change from 1995 is that ocean worlds are much more common than we thought then. What this really tells us is about the thermal evolution of these bodies. How did they keep warm enough to maintain oceans over geological time? And then finally, dynamos were common in the past. And although most dynamos we think are driven by thermal convection, in the case of the moon, it may have been mechanically driven, not driven by thermal convection. Okay, are there any general lessons to be learned from all this? Well, it's hard, but I came up with 2. And the first is just, it's pretty obvious, but physics is universal. The great thing about geophysics is that once you understand the processes, you can take that set of processes and you can apply them to lots of different bodies in the solar system. The physics doesn't change, the parameters will change, but there's a big advantage in being able to hop from one solar system object to another because of the universality of the processes. And then the other one is that although spacecraft measurements are incredibly important, they're not the only things that matters. And one of the points of these surprises is that both lab measurements and theory have played an important role in these these developments. And so observations are important, but they're not the only thing. Planetary Science is in a pretty healthy state. This is a selective list of things that are going to get launched in the next few years. We're going to Europa, we're going back to Titan, we're going to the moon again, we're going to asteroids. So there's a great deal going on. And the other thing that you notice is that unlike 25 years ago, it's not just NASA. There's ESA, there's South Korea, the United Arab Emirates have launched a spacecraft. And so it's a much more international enterprise than it was 25 years ago. So I think planetary exploration is in a healthy state, and it's become much more international. I do think, though, that the outer solar system is underexplored, and that's mostly because it's hard to get there. So I'm optimistic, and I think that we're going to get plenty of surprises in the future. So just to wrap up, I wanted to express my thanks to a couple of organizations. The first two are Magdalen College and the Royal Society. And both of these gave me financial support with really very few strings attached. And so they didn't care that I wandered off to the States and spent time there. And so I'm extremely grateful to them for their support at an early stage in my career. And then more recently, I'm very grateful to NASA for their continued support, but also because of their enlightened treatment of foreign participating scientists. The only reason that I got into planetary sciences is because my future PhD supervisor was allowed to join a NASA mission, even though he wasn't American. And so I would like to highlight that as a very enlightened policy. I personally have benefited from it. And then finally, I would like to thank 4 professors who've been particularly influential in my life. First, of course, there's my PhD supervisor, Dan McKenzie, who has a brain the size of a planet. Somebody else who has a brain the size of a planet is Dave Stevenson, who was my postdoc advisor. And then I'd like to thank Dave Gubbins for being very influential, and in particular for convincing me that actually thinking about the Earth as a planet was a reasonable way to spending my time. And then lastly, there's my wife, Emily Brodsky, who has been a continual source of support for almost 20 years at this point. So I'd like to thank all of those 4 very much, and thank all of you for attending. And I'll leave it there. Thank you.
Thank you very much, Francis. And we have a number of questions that have come into the chat. And if I start from the top, as a question from Jerome saying, today's lunar core rotation axis is essentially aligned with the normal to the orbit, so very much tilted. How do you reconcile this with your precession mechanism, requiring core and mantle rotating to be well coupled to switch off the dynamo?
So I would like to know how the speaker knows that the core rotation axis is aligned with the normal. It's not obvious to me that that's the case. Maybe he can reply in chat and we can have a conversation.
Okay, Jerome, if you send another message through, then Francis will see it. The next question is from Q Stanley, and he says, when you mention oceans, I take it you mean more than H2O, and as such, does the tectonics vary with the type of ocean and thus the dynamo from your argument?
So when I say oceans, I do actually mean mostly water, although there may be other things in them like salt or ammonia, and those contaminants are important because they reduce the freezing temperature. And so if you add a contaminant, it actually makes it easier for an ocean to survive. In the case of the induction experiments, it's clear that the oceans have to be salty because a pure liquid water ocean wouldn't be conductive enough.
Thank you. And the next question comes from John Zarnecki. I hope I've pronounced that correctly. And John writes, if we were to give you one spacecraft, just one, where would you send it and what would it do?
Okay, so I think what I would do is I would go to Enceladus, which is this small moon of Saturn, because Enceladus is blasting water vapor into space. And so it is giving us free samples of its interior. And so if you really want to understand what the interior of a body is like, you want to go to Enceladus and bring samples back, because there you're actually getting free samples from the interior.
Brilliant. And the next question is from Simon Josie, and it's great talk. Can induction usefully be employed to determine to some extent the chemical composition of the interior ocean moons?
Right, so that's a great question. If you can measure the induction response at several frequencies, then you can get the depth of the ocean and the conductivity of the ocean independently. So it is possible to get the conductivity of the ocean. The problem is relating the conductivity to the composition, because you can imagine there are different contaminants that might give you the same conductivity. And so you can get the conductivity, that's easy. Getting the actual composition is harder unless you have extra information, like, for instance, spectroscopy at the surface.
Thank you. And the next question comes from Stephen King, who writes, I like the cooling history infers oceans idea. What is the basis for the amount of heating radioactivity assumed in your cooling models? How do we think that radioactive elements are distributed through the solar system?
Right. So the best evidence we have is that if you look at the most primitive meteorites, you can see their elemental concentrations. And if you look at the sun, the stellar photosphere, you can look at the elemental concentrations there, and they are the same. So the elements are in the same ratio in the primitive meteorites and in the sun. And so that's suggesting that that is the original material from which the solar system was made. And so if we don't have any other information, we assume that the radioactive elements are present in those proportions. And that's probably a pretty good assumption in the outer solar system, at least.
Thank you. And the next question from Paul W. is there any, open brackets, externally closed brackets, detectable frictional heating with subsurface oceans?
So I'm assuming that this means, is there dissipation in the oceans just like there is on the Earth? The Earth's oceans dissipate quite a lot of tidal energy. This is somewhat controversial. I think most people have decided that tidal heating inside oceans is not important compared to the tidal heating in the solid objects. But there is not universal agreement on that, if that's what the question was asking.
Okay. And Tanya has said, great talk, thank you. Jerome, who asked the first question, and you asked, how do you know it's aligned? And he's replied and said, from theory.
Yeah, so I think if you look at, there's a Goldreich paper slightly after that looks at exactly this question and concludes that it went from processing around the invariable to co-processing with the mantle at some point in the in its orbital evolution. So I can pull out that Goldreich paper. I just don't remember the year off the top of my head.
Yeah, he's mentioned Poincaré, if that's how you say it, 1910, or Booth, 1968.
Yeah, the Goldreich paper was a little after that.
Yeah. Richard Katz has asked a new question, which is regarding Pluto and TPW. In your model, the deposit of solid nitrogen seems to not be isostatically compensated. Is that right? Why not? Why would the talk on the ice shell be affected about the denser water that is isostatically uplifted from below?
Yeah, so that's a good question. What's happening is that immediately after the impact, you get isostatic compensation. But then if you wait, then the shell will cool and become rigid. And then at some later time, if you add nitrogen on top, the nitrogen will be supported by a flexure, by the elastic strength of the plate. And so that's how you end up with a positive gravity anomaly. And it's not that the torque is acting on the water itself. It's just that the moment, the degree 2 moment, which is not what you care about, depends on the overall gravity anomaly. and that's really being controlled by the solid nitrogen. That's where the mass excess is coming from.
Thank you. The last question I have in my list for you at the moment, until someone asks some more, is the tidal heating detectable in the surface anywhere it is intense enough?
Yeah, so right now there are only two places where we've detected tidal heating directly. One is Io, where the surface heat flux is sort of 10 times the Earth's surface heat flux. And then the other is Enceladus. The south pole of Enceladus is anomalously hot. And so that is the other place where we're actually detecting directly tidal heating being created. So those are the two places where we've actually detected tidal heating.
Cool, thank you. I suppose cool might not be the appropriate phrase where you've got tidal heating, but there you go. My personal question is Mercury's core. Can you say a little bit more about that, please?
So the most important thing about Mercury's core is that it's huge. There's only a thin skin of mantle on top. And so we don't actually understand why Mercury's core is relatively so much larger than that of all the other terrestrial planets. That's a big puzzle. The other thing about Mercury's core is that the dynamo it creates is very weird. The center of the dynamo, as it were, is off axis. It's off center. And so that's not well understood. It's as if, yeah, so there's something very peculiar about the circulation pattern in Mercury's core that is not well understood.
Brilliant. There is one question that Mike might be able to answer. It comes right from the beginning. It regards the thesis awards, and the question was, is the thesis proposed should be done in England?
Thank you for that. So far as I know, Great Britain, I think the United Kingdom, but I'm not absolutely sure about that, and we should follow that up. It will be it's on the RS website. We'll give you the details.
Thank you. And another question is coming for you, Francis, from Stephen King. It says, have you read 20,000 Leagues Under the Sea, and are you an example of nominative determinism? P.S. Thanks for a great talk and Q&A.
So I read 20,000 Leagues Under the Sea a long time ago, and I'm afraid I don't know what nominative determinism means, and so someone will have to explain it to me.
It means that your name determines your occupation, so that a Mr. Baker works in a bakery.
People have made jokes about finding Nemo over the years.
Shall I take over and add my thanks to that for a very clear, a very entrancing lecture, obviously provoking many interesting questions too. Nobody sort of commented on the planets more complicated than stars. Well, I think we could have an excellent discussion of that one. Galaxies being even simpler and cosmology just being nothing at all. So anyway, thank you very much for a wonderful, wonderful lecture. And I also have to announce, I give notice that the next ANG open meeting of the Society will be on Friday, the 10th of December. Thank you very much, everybody.